So the next example is the Haber process, so the production of ammonia. And we are given these three values. Now remember, these are the equilibrium concentrations. So when you do the Haber process to make ammonia, at the very start, you'll only add in nitrogen and hydrogen. So at the start of the reaction, you will have some concentration of nitrogen, some concentration of hydrogen, and you won't have any ammonia. So if you were to use those values, the initial values, you wouldn't be able to do the equilibrium constant. So the equilibrium constant must be calculated using the equilibrium concentrations. All right, so we put nitrogen, we put hydrogen in, we allow it to react to produce some ammonia, and once the concentrations of all of these are stable, so they're not changing, then we can measure the concentrations and use that to work out the equilibrium constant. So for this reaction, Kc is going to be, remember it's the products divided by the reactants, so it's going to be NH3, and I've got a 2 in front of there, so that's squared, divided by the concentration of nitrogen, multiplied by the concentration of hydrogen, and the hydrogen has a 3 in front of it, so this is going to be cubed. Okay, now this is the easy part. So now you just take these three numbers and put them into the equation. Okay, so there's no problem doing that. All right. Just before we do it though, you can see that the concentration of nitrogen is really, really large. All right, and then these are kind of similar. Okay, so I'm expecting we've got large concentrations over here, not so large concentrations over here. I'm expecting a Kc value of less than 1. Okay. So if we put it in, it's going to be ammonia is 1.5 squared divided by N2, which is 18.6, multiplied by H2, which is 0.9 cubed. Okay, and you can work that out and you should get 0.166. Now the question is the units. Now, when you read the book beforehand, you'll have noticed that they gave these strange units of decimeters to the power of 6, moles to the minus 2. Okay, so how do we get that? Right, well, we just do the exact same analysis as we did before. All right, so the units of concentration for this are moles per decimeter cubed. So it's going to be moles per decimeter cubed squared, divided by, well, the concentration of nitrogen is in moles per decimeter cubed. And the units for H2 are also moles per decimeter cubed. But that is now cubed. Okay, so we can simplify this to moles per decimeter cubed squared. And then here, we're multiplying this by this, so we add the powers. So we have moles per decimeter cubed to the power of 4. Okay, now we can cancel this, cancel that down, so that's a 2, which gives us 1 divided by moles per decimeter cubed squared. Now at this point, we can now put the 2 inside the brackets, so we have 1 divided by, well, it's my moles squared, all right, and then remember, if you've got x to the power of a to the power of b, that equals x to the power of a times b. Okay, and here I've got decimeters to the minus 3 all squared. So it's going to be 2 times minus 3. So I get decimeters to the minus 6. Okay, now it's the reciprocal of that, so it's 1 divided by it, which means that all of the powers become the negative of what they are here. All right, so hopefully you remember that 1 divided by x equals x to the minus 1. and 1 divided by x to the a equals x to the minus a. So all we do is we just take it as moles to the minus 2 decimeters to the power of 6, which is how they get the units they use in the book. All right. Now, you will need to be able to do this at some point. Okay, so it's not covered in the course at this particular point, but it is going to be in the next topic. All right, so we will have a lesson where we'll do a little bit more practice of this. So it's good if you can be able to do this now. So yes, my equilibrium constant is less than 1, as I expected, and that's about it really. So these things are quite straightforward to calculate. The units are a little bit tricky, but it's the interpreting it is the important part. Now, there are two things that we need to talk about, which are that the value of Kc is affected by temperature. Which we'll talk about more in the next topic. And also, Kc is unaffected by changes in concentration. Now, if you think about this for a little bit, you might want to pause it and have a think about this. This should be a little bit confusing, because all the way through the topic on Le Chatelier's principle, we talked about changing the concentration, changing the position of equilibrium. Whereas now I'm telling you that if I change the concentration, the equilibrium constant, which tells you the position of equilibrium, doesn't change. So, well, which is it? What am I talking about? All right, so I can illustrate this quite nicely with one final example. Okay, so we're just going to do one more example, which is this one. Okay, so this is example number 3. Now, I can use these values to calculate my equilibrium constant. So Kc is going to be the concentration of NO2 squared divided by the concentration of N2O4, which is NO2 is 0.4, so it's 0.4 squared divided by 0.01. So if I work that out, I'm not sure if you can see my calculator. Oh, there it is. 0.4 squared divided by 0.01 gives me 16. And the units for this are moles per decimeters cubed, because 2 is cancelled by that, so you just have the units of concentration. You can work it out all the way through if you want to. Now, that shouldn't be a surprise, because the concentration of NO2 is much larger than the concentration of N2O4, so we'd expect this value to be larger than 1. Now, if I was to increase the concentration of N2O4, what would you expect to happen? Well, I've said before that if you increase the concentration of this, the position of equilibrium shifts to minimize that increase. So it will favor the forward reaction, producing more NO2. Okay? So if I increase the concentration of this, I will increase the amount of NO2 that I get. Well, we can try it now. So let's say that I, increase the concentration of N2O4 from 0.01 moles per decimeter cubed to, so we had it here 0.01, let's increase it by 10 to 0.1 moles per decimeter cubed. All right, so what is the concentration of NO2 once equilibrium is established. Because obviously if I change one of these quantities, if I change the concentration of this, it's no longer in equilibrium, so you have to wait for it to get to equilibrium, and then we can work out what the concentration of NO2 is going to be. All right, so let's say we have now Kc equals NO2 squared divided by N2O4. Right, now I know that at equilibrium, that value has to be 16. Okay, so I can say, well, 16 equals NO2, my concentration of NO2 squared, divided by my concentration of N2O4, which I've increased to 0.1. And now all I do is I solve for NO2. Okay, so the concentration of NO2 is going to be 0.1 times 16, which is 1.6, and the square root of that. So if I do the square root of 1.6, what do I get? 1.26. 1.26 moles per decimeter cubed. So you can see that when I had 0.01 moles per decimeter cubed of N2O4, I had 0.4 of NO2. All right. Then I increased N2O4 from 0.01 to 0.1, and I've increased my NO2 up to 1.6. So you can see that even though the equilibrium constant stays the same, it means that if you change the concentration of one of the reactants or products, it will change the concentration of the other one as well. Okay.